My name is Yicheng Zhang. I'm from UC Riverside. Today, I'm happy to introduce our work. It's all in headset, side-channel attacks on AR/VR systems. This work was done with my colleague, Dr. Slocum, Professor Chen, and my advisor, Professor Nael Abu-Ghazaleh. Probably introducing AR/VR system again. So the first president already introduced it. So these kind of systems are everywhere. So I guess this year everyone got impressed by the performance or the prices of the Apple's Vision Pro. But the market doesn't only have the Vision Pro, they have various of kind of AR/VR headset like the Microsoft HoloLens or Oculus, so on. And this market actually increasing to be really large this year already, $16 billion this year. And it will increasing with high speed actually. This is my outline for today's work. I first introducing the architecture for AR/VR system, and then introducing our threat model and the leakage vectors. And then I'll walk you through three kind of side-channel attacks, and then talking about the mitigations. Okay, starting from the AR/VR system, hope this diagram does not scare you too much. So let's starting from the bottom to top. So the bottom layer, which is the hardware, typically contains a series of sensors and computer engines taking care of the input and output. For the middle layer, which is AR/VR SDK, so they're not only providing some basic management API for the bottom layer, but also providing some functions for your upper layer. And then it's the top layer, which is developed tools. The developer can design their own AR/VR application in this layer. In this work, we focus mostly on the rendering performance counter, so lies in the middle layer. So it's similar to the CPU or GPU performance counter. So it helps users to track the performance of their AR/VR applications. And the user with normal permission, they can access to them. And the system providing like hundreds kind of counters to access. And then I was introducing our threat model. So we assume there's a software side-channel attacks in this system, which means that there will be a malicious program running in the background. So this malicious program can be downloaded from App Store or somewhere else. And this program only has the normal permission as normal user. Absolutely, they will have no physical access to the device or the other users. However, the spy application will keep probing the rendering performance counter, and then it will leak some information about the victims. So one question. So what kind of leakage vector we can measure in this work? So first introducing one easy vector, which is memory allocation API. It's a simple API, you just need to query it, you got the memory usage. And then next one, your rendering performance counter. I introduced it before, so they're provided by the Unity and Unreal SDK. The first kind of is like framework. So for example, it's kind of like the frame rate at frame per second. It can tell you how your VR game runs smoothly or not. Second time is like relate to a thread, tell you how many times for each thread times. And then it's relate to the render text. You want to know how your digital world looks like, how many like vertex count it is, and so on. And then I'll introduce the overview of our side-channel attacks. So basically, in all these three kind of attacks, we assume the spy application running in the background, profiling the leakage vectors. The first kind, we try to spy something on the user interaction. It can be hand gesture or voice input. And then we also try to do another scenario is that victim may launch some concurrent application together with the spy application. So we want to do some probably bad thing on the concurrent applications. And last scenario is that probably we can do something bad in real world. So for example, this time can be a bystander, and we try to infer some private information about bystanders. Okay, and introducing about like our experimental setup, we're testing all attacks on two popular headsets. One is for AR and another for VR. 10 volunteers involved in this attack. And this is our attack workflow. After we collecting the side-channel leakage, we throw them into the feature engineering module and extracting some interesting features. And then we throw them into some classifier or regressor for each specific AR/VR task. Okay, let's start from our first attacks to infer the victim's hand gesture. So in this attack, so probably the victim try to communicate your AR/VR devices with the hand gesture. But at the same time, there's a spy application running in the background, also collecting the side-channel leakage. And we find that this kind of leakage correlates with the victim's hand gestures. So let's take a look at the raw performance counter traces we got. So the counter we use here is the vertex count. So actually, to note here is that I only show just one counter, but actually there are tons of counters that are available in this work and also in the SDK. So this one just showing one case, we can have one counter for signature for that. And they actually have three different hand gestures, start menu, touch, and air tap. They have totally different computer performance counter traces. because they're different, so it gives us a chance to do the classification for what kind of hand gesture the victim are using. So actually, we profile 5 different hand gestures on 2 devices. We train some normal standard classifier for the inference attack, and I find the performance really good and almost like 90% accuracy for the F1 scores. Okay, second attack. So this time maybe the victim is kind of lazy, so the victim don't want to using the hand gesture, but using the voice command to communicate with the hand gesture your VR devices. Similarly, there's a spy application running in the background, keeping measure the performance counter, and we find the performance counter also correlated with the content performed by the victim. So here we use the one showcase, which is your memory allocation traces provided by this API, and we find that different voice commands have different memory pressure on the spy applications. Similarly, another 5 voice commands are provided on 2 devices. The same classifier used to train that, and we find like over 93% for this attack or 2 devices. Okay, next our third attack. So we do the keystroke monitoring. I think it's a kind of standard attack. I always see a lot of attacks doing the similar things. So victim trying to enter something on the keyboard, and then also the spy application running in the background and try to identify what kind of digit the victim is typing. This is the 2 counters we're using, is the game and the render thread time. As you can see, we can identify when the victim pressed the digits, and after the rendering for digits finished, it stabilizes after that. And because the digits, they're located on different places on the virtual keyboard, so they have different hand movement. So using the performance counters, we can differentiate them. We provide like 10 digits on the HoloLens Quest 2, similar methodology using to train them, over 90% accuracy for them. Okay, next move on to the fourth attack. So it's another scenario. So the victim is running some concurrent application, and the spy actually want to identify it. So actually to note here is so this attack can be combined with a previous attack. So the spy probably can firstly identify you launching some private like application, for example, a banking account, and then do the keystroke to infer your password. So there's a performance counters traces for 3 different applications. They have total different patterns for the counters. Similarly, we got like around like 90% accuracy for this attack. Okay, last attack. So this time actually the victim will be the bystander who step into view of the AR/VR devices. But at the same time, the spy side, he will not only profiling the performance counter, but also forcing the device to generate the spatial mesh of the surrounding environment. So when the bystander step into the view, so the AR/VR device will also generate spatial meshes around the bystanders. So this gives us a chance to infer like some private information about the bystanders. So in the end, we turn an AR/VR device into a surveillance device. So this is the performance counter traces. Here we're using a CPU frame rate. And you can see there's a distance-dependent fingerprinting for different distance. And also we can also identify when the bystander step into the view and when the bystander step out of the view. In this attack, we're using some regressor rather than the classifier to do the bystander estimation attack. So we can see there's only like 10 centimeter error for our attack. Okay. Actually, we already demonstrated, okay, probably the performance counter is leaky and they're kind of dangerous. So think about how we can mitigate this kind of leakage. So there's one naive way is to we're completely blocking access to this leaky API or counters, but that sounds unreasonable because developer or the user, they need these counters to tune or optimize their performance of their applications. So we think about another way is that we're limiting the sampling rate or the precision of your performance counter, but it seems not very effective. So the evaluation shows that even though we downgrade the sampling rate from 60 Hertz to even 1 Hertz, we can still infer something with over like 50% F1 score for hand gesture inference attack. So mitigation seems not very effective for this attack. So let's wrap up. So actually, our work is the side channel attacks on AR/VR systems. We're the first one to using the performance counters. And we actually demonstrate 5 end-to-end side channel attacks in 3 different AR/VR scenarios. And we also do some mitigation evaluation, but it seems that mitigation using the limiting your sampling rate is not very effective. Okay, and also it's some future work. So Actually, our attack is on thinking about like single user or single devices. But how about like multi-user AR/VR system? How will the performance counter will be applied to these systems? How can we defend that? Another way is like, can we ask the defense side? So can we have a better profiling system for AR/VR? I know something like for the NVIDIA, they're providing the mix system for the A100, H100. So you can have a very accurate but also secure profiling system for your GPU usage. So can we have another like similar profiling system for AR/VR devices? That probably we can need some help from the system like expert on that. Okay, that's all my work, and I'm happy to take any questions.